There is this famous quote from the movie Interstellar, when the protagonist says, "1 hour here is 7 years on Earth." That means time passes more slowly on the planet they are on. Is this theoretically possible or just pure fiction? In order to answer this, let us dive into the concept of special relativity and time dilation. Albert Einstein's theory of special relativity begins with two groundbreaking ideas, two simple yet profound principles that changed the way we understand the universe. First, Einstein realized that the laws of physics are the same in all inertial frames of reference. This means that no matter how fast you're moving, as long as you're not accelerating, the fundamental rules of the universe don't change. Whether you're standing still or flying through space at a constant speed, the same physical laws apply. Second, and equally astonishing, is that the speed of light in a vacuum is constant for all observers. Regardless of how fast you're moving relative to the source of light, the speed of light remains the same for everyone, everywhere. Now let's do a thought experiment. Imagine two observers. One is stationary, and the other is moving at a constant velocity. Let's call the first one A and the second one B, where observer B is therefore moving at a constant speed relative to A. In the vehicle B is moving in, there are two mirrors positioned vertically. Between these mirrors, a pulse of light is bouncing up and down. For B, the mirrors and the light are moving along with them, so the pulse of light only moves in the vertical direction. From A's perspective, the light pulse travels with B, so it does not only move in the vertical direction but also moves in the horizontal direction. This difference in perspective is where time dilation starts to emerge. Let's first focus on what B observes. Because the mirrors and B are moving in the same vehicle, from B's perspective the pulse of light only bounces up and down. Let's call the distance between the two mirrors L. The time it takes for a pulse of light to bounce up and back down then equals the distance it has to travel divided by the speed with which the pulse moves forward. In this particular case, it therefore equals 2 times L over C. For observer A, the light pulse is following a diagonal path, longer than the vertical path seen by B. But the speed of light remains constant. This creates a challenge. From A's perspective, time must slow down. This allows the light to cover the extra distance without breaking the universal speed limit, the speed of light. We can understand this using geometry. From A's viewpoint, the light travels along two diagonals. The distance the light pulse covered vertically is equal to 2 times L. The distance it traveled horizontally is equal to the speed with which observer B moves, multiplied with the time it took for the light to bounce up and down. Note that therefore the length of this path is equal to the hypotenuse of the right triangle with sides 2 times L, and the speed with which B moves multiplied with the time it takes the light pulse to bounce up and down, seen from A's perspective. Now we can use the Pythagorean theorem to calculate the distance the light pulse traveled. But the distance the light pulse traveled must also equal the time it moved times the velocity with which it moved. Hence it also equals the speed of light times the time it took for the light to bounce up and down. Combining the two expressions and rewriting them gives us an expression for the time elapsed from the perspective of observer A. Now we know two things. From B's perspective, we can express L in terms of C and the time elapsed for B. From A's perspective, we can express the time elapsed from A's perspective in terms of V, C, and L. Substituting the two and rewriting the equations finally gives us the relation between the time from B's perspective and the time from A's perspective. We started with two fundamental principles. The laws of physics are the same for all inertial observers, and the speed of light is constant for everyone. These two ideas led us to the conclusion that time itself can stretch or dilate depending on how fast you are moving. For a stationary observer, time ticks at its normal pace. But for an observer moving at high speeds, time slows down. This means that time is not an absolute, fixed quantity. It depends on your motion through space. This has profound implications for our understanding of the universe. Time dilation means that astronauts traveling close to the speed of light could experience hours, while years pass on Earth. It reveals that time and space are interconnected, fluid, and relative to each observer's motion.